Hello, today I'm going to walk you through a mass selection experiment. I will select for length in Danny Aurelio, zebrafish. The first thing I do is measure my zebrafish. I arrange the zebrafish into a histogram here. Using this data, I calculate my mean and standard deviation. I also do some research and find that for lengthened zebrafish, the broad sense heritability is 0.85 and the realized heritability is 0.67. My mean is 45 millimeters with a standard deviation of 3.2 millimeters. I'm going to select the top 10% to breed, and this proportion tells me which I and Z values to use as highlighted on this table. In my research, I also find that zebrafish length is normally distributed, so without breeding fish, I can calculate the mean of the offspring. First, I need to find the truncation point x sub t. This is my cutoff point. The fish longer than x sub t are the ones I will separate for breeding and are indicated by this shading. This is also the top 10%. To find the truncation point, we will use this formula. We already know the mean, z-value, and standard deviation, so we can plug in those values and we get that x sub t is 49.1 millimeters. We can label our graph with that, and now I know to separate all fish longer than 49.1 millimeters for breeding. Next, let's find the mean of the selected parent fish. We can find this with the following formula. The mean of selected parents equals the mean of the population plus the selection differential. We don't know the selection differential, but we can find that as well using this formula, which says that the selection differential is the selection intensity times the standard deviation. We know both of those values, so we can plug them in to find that the selection differential is 5.6. Going back to the formula for x sub s, we plug in mean and selection differential and find that the mean of selected parents is 50.6. We can add that to our graph, and the distance between x sub s and x naught can be labeled with the selection differential, since that is how we found x sub s. Next, I want to know the response to selection. We can calculate this using realized heritability, which is equal to r over s. We can rearrange this formula to say that the response to selection is the realized heritability times the selection differential, and we have both of those values. When we plug them in, we find r to be 3.8 millimeters. We can add response to selection to our graph right here. Now I want to calculate the mean of the offspring, x sub 1. To find the mean of the offspring, we use the following formula, which says that the mean is equal to the mean of the population plus the response to selection. We know both of those values, so we can plug them in and find the mean of the offspring to be 48.8 millimeters. So without doing any breeding, I know what the mean of the offspring will be. Can I keep repeating this experiment to get a 1 meter long zebrafish? Not practically. In existing mass selection experiments, scientists saw a point at which they could not breed the population past a certain point. Most notably, they could not make mice any smaller since the smallest mouse was sterile. These limitations may come from genes linked to the desired trait that result in adverse effects to reproduction or mortality rates.